Alright, what's going on everybody? In this video we are going to be talking about related rates. Now, a few years back when I was taking Calc 1 or AP Calc in high school there, the two hardest things in that entire class was optimization and related rates. At least for me it was, right? And I know that's the same for a lot of you. Related rates is a tough topic. And so in this video I just want to go over, everything related rates. I want to give you guys a full introduction, right? I want to talk about chain rule, implicit differentiation, and lead that up to related rates. And then we're going to do a lot of practice problems with related rates. All right. So I have the timestamps right here. Basically I'll just give you that intro to start out with, okay? And then we will just do that quick review, that much needed review of implicit differentiation and chain rule, okay? This might not seem like it's that needed, but I promise you, for a lot of you, it's going to be extremely helpful. But if you've already reviewed this stuff, you already feel like you have a really good grasp with this, you just really want to tackle the problems, well, I have the problems right here as well as all the timestamps for those guys, okay? So, if you're looking for something specific, like we're doing an example with a sphere, I know a lot of people struggle with ladder problems. We have cones, like a circular cone tank, right? Water, that's a really popular type of problem. Two cars is another big type, another thing that you can fill up with water, and then we're going to do some trig as well, so how an angle changes with time. Okay, so a lot of stuff here. Let's get into it. Okay, so first I want to start out with a quick introduction to related rates, right? Before we even get into any of these practice problems, we got to know what we're actually finding, right? What we're actually doing with related rates. And so what I have written down here is that in a related rates problem, we are given the rate at which something changes. Okay, that's what we're given. And our goal is to find the rate at which another thing changes. Okay, so we get the rate at which something changes, and our goal is to find the rate at which another thing changes. So we are relating two rates. Okay, here's an example, and I just want you to tell me here, what are the two rates that we're going to be relating? Okay, so here we have a spherical water balloon is being filled with water at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when its current radius is 25 centimeters? Okay, or maybe that wording is a little weird. So I'll say when its radius is 25 centimeters, how fast is the radius of the balloon increasing? Okay, so, and there should be a question mark here. All right, pulling everything together here. There is two things that we are relating here, right? Two rates. One of the rates is the rate at which the spherical water balloon is being filled with water, right? That's here. We have centimeters cubed per second, right? That is, maybe you can see that's the rate at which the volume is changing in time, right? It's the volume per second, volume per time. All right, so we're relating dV dt to, we want to see how fast that radius is going to be increasing, right? And that is dr dt. So these are the two things that we want to relate. We have dV dt, and now we want to come up with an equation, do some calculus, and come up with what dr dt is going to be. All right, so that's the idea with related rates, okay? So now that we have that out of the way, we understand, what our goal is for this related rates unit. Let's talk about implicit differentiation and chain rule. And we'll start off with chain rule. I'm going to do a quick review here. Now, with chain rule, right, you're probably used to seeing a formula like this. It's really gross, kind of hard to understand, but the gist of what you really need to get out of this is that when you take a derivative of, something inside your function, like, for instance, with this exponential we have as an example, we have a 2x instead of an x, right? And so that g of x would be 2x. But when you have to take the derivative of a f of g of x, right, of a function inside a function, you take the derivative of the outer function, leaving whatever's inside alone, right? You leave the 2x alone. And then you multiply by the derivative of the inside function. You take the derivative of the 2x and multiply it on the outside. Okay? So what we can end up doing here, right, we can see that this would just give us that, y prime, that the derivative with respect to x here would be 2e to the 2x, right? If we take the derivative of the e to the 2x just like it was an e to the x, we get this piece, right? That's just the e to the 2x. That's the f prime of g of x. And the 2 comes from g prime of x, right? That's the derivative of what's in the exponent, okay? But I want to do that a little bit different, right? I want to show you that kind of a little more rigorously, I guess. Maybe that's the right word to use. I want to show you it with like more notation, because the notation is what we're going to need for related rates. So what we could have also done is we could say let u equal 2x. Okay, so now we have u being a function of x, right? So we can even write this as u of x equaling 2x, right? So now we have that y equals e to the u. Okay, so if we want to take a derivative on both sides, which we do by, right, we're taking a derivative with respect to x, so we put our derivative operators on both sides, right? If you're unfamiliar with that term, derivative operator, right, the d over dx thing just tells us that we want to take a derivative of whatever's inside here with respect to x, okay? So that's the idea with that. Now, the derivative here is just going to be dy over dx, right? When you take the derivative of y with respect to x, you get dy over dx. Okay, cool. But what about this derivative of e to the u? Okay, well, we know that, e to the u, right, that is what y is, okay? And so what we would need to do here, we can split this up because this is a u, this isn't an x, right? And so we need a dy and a dx on this side. But we can't get that right away. And so what we do is we first take a derivative with respect to u, right? Just like, so it's basically like the same thing as this right here. All right, we take a derivative of the outside. And then we take a derivative, since this u is a function of x, we take a derivative of that u with respect to x. That's equivalent to the g prime of x. Okay, so that's another way, and then you can see here the du's cancel and you're left with dy over dx, which is exactly what this other side is. Okay, so that's another way that you can write it out with notation. Hopefully that's not too confusing. But if we can keep going further with this, right, we get that dy over dx is equal to, we're going to separate this now, right? So instead of writing it as dy over du, I'm going to separate out the operator, right? Remember what I said before with this stuff. Separate out the operator and just have a derivative with respect to u of y. And then we're going to multiply a derivative with respect to x of u, right? That's just this piece. So you have a derivative with respect to x of u. Cool. So we know that y, right, if we just keep going here, we know that y is e to the u, right? And we know that u is 2x. And so taking a derivative with respect to u, we would get e to the u, or if we want to write that in terms of x, right? We know that u is 2x, so we'd put that there. And then the derivative with respect to x of 2x, well, that's just going to give us 2, right? And so we'd have times 2. You could write that as, I could erase this whole thing and write it as, instead, dy over dx equals 2e to the 2x, right? And that's exactly what we got up here. So basically, I just showed you the exact same thing, but now we did it a little more, with a lot more notation, making it look a lot more rigorous, right? A lot harder. But I promise this is actually going to be useful. Okay, so let's do just one more try with this. If you feel pretty good with this, you just want to move on to implicit differentiation review, that's fine. But here's another example where we do this. Okay, so if we, right, we have a cosine and we have a 2t squared on the inside. So let's let u equal 2t squared, take this derivative, okay? And we write that dy over dt, okay, and so u is now a function of t, right? So we can write this as right there, okay? dy over dt is going to be dy over du, right? Just the derivative with respect to u, because now if we rewrite this, we would get that y equals the cosine of u, right? So we want to first take a derivative of the cosine, like normal. We're just treating this u like we would treat an x in a regular derivative with respect to x, right? So we're just treating it in the same exact way. Now, we have to multiply here, right? We want to get a dy over dt, right? And so what we do is we multiply by a du over dt. The du's cancel out, and you see the dy over dt. Okay, so there's two different derivatives that we have to deal with here. We can just start using some notation. All right, we can start splitting this up. And what we're going to do is just write this as d over du of y. Actually, scratch that. I'm going to write dy over dt equals, right, the derivative with respect to u of y. That's what this piece is saying. Times the derivative with respect to t of u. That's what this piece is saying. And then we just plug in what those are, right? The y is equal to cosine of u. And u is equal to 2t squared. Okay? So then we keep going here. The derivative with respect to u of cosine of u is going to be negative sine of u. Instead of writing u, we can write 2t squared, right? Just sub that back in already so we don't have to do it later. And then if we take the derivative with respect to time of 2t squared, we get 4t. And so we get that dy over dt is equal to negative 4t sine of 2t squared. All right? So, again, this is going to be important, right? The reason I'm not doing all this notation just to mess with you and throw something a little bit harder and make you confused with chain rule. The reason why I'm doing this is because it's going to help with implicit differentiation, and implicit differentiation is going to really help with related rates, okay? So, moving on to implicit differentiation here, okay? The main idea is that, what if we wanted to find the slope at any point of a curve, right? So we want to find the slope of a curve that can't be written or would be tough to write as y as a function of x. So a great example of this is a circle, right? A circle can't be written as y equals a function of x, right? You may be thinking, oh, well, you can write it as like a y equals plus or minus kind of thing. Well, yeah, but now you're writing it as two separate functions, right? You have a plus one and then you have a minus. So it's not an actual it's not just one function of x that you'd be writing. So this is not going to be a function. And so we're going to need to do implicit differentiation on this. And before we do that, I do want to note some terminology here, because this is something that you may have been confused on. I was very confused on it when I was in Calc 1. Okay, and actually I didn't know this, and so this actually ended up following me until pretty much this year, and I'm a junior in college right now. So I finally figured out what an explicit function and an implicit function are, and it took me to like a higher level physics class to finally have to realize what those are. So when somebody says an explicit function with your teacher or whatever, basically it means that you have x's right here, right? If y is an explicit function of x, it's y as a function of x, right? But if you have y as an implicit function of x, that means you have x's and y's kind of mixed together, right? On the same side, they're all mixed together. Okay? And what you can end up doing in this case, right? You're just kind of implicitly, or you're implying, right? Implicit implying, right? That y is a function of x, right? And in the case of a circle, we can't write y as a nice function of x, so we kind of just write it in like that, okay? And so what's going to end up happening here is, this is kind of like the u as a function of x from before, right? From when we were discussing chain rule, right? And we had to chain rule it like this. That's what's going to happen with implicit differentiation. Okay, and so I will show you that here in just a second when we actually do this implicit differentiation. Okay, so we want to find the slope of x squared plus y squared equals 4 at any point xy. Okay, so what we're going to do here, right, we're going to write out this equation. Okay, and I have this spaced out for a reason. So, like always, right, when we're trying to find the derivative and we have x as our, our main independent variable, that's what we can do here, we can just take a derivative with respect to x on both sides. Okay? When you do that, you can split up these terms using our derivative rules, right? We can take the derivative of each piece separately. And remember, this is y of x squared, right? It's a function of x. Okay, and on this side, it's 0. Okay, and when you take this derivative, right, we know that you get 2x. But what about right here? Okay, well, think about it like this. Think about it like what we just did with chain rule. And this is when I said it was going to come in handy. I promise it was, right? If you set b equal to y of x, okay, and you take a derivative with respect to x on both sides, how do you do that, right? Well, you say that db over dx is going to equal, well, first, if you want a db over dx on this side, right, you need to first take a derivative with respect to y, right? Because really here, you're going to have some expression of y's, like maybe a y squared. In this case, we just have a y, right? But you need to, and like over here, we have a y squared. And it looks a little weird because it's written in this notation, but this is what I mean, right? We have a y squared. But first you take that derivative with respect to y, and then to cancel that dy, you write a dy over dx, right? And that's how I like to think about it, because then you have a db over dx on both sides. All right, and so think of this as the derivative of your outside function and the derivative of your inside function. Okay, so how do we translate this, right? What does all this notation crap mean? Well, db over dy, right? That's just going to be the derivative, like we were, think of this now as y squared, because it's a little nicer to look at. Okay, take the derivative of it normally like it was an x. We would get 2y, right? Now multiply by the derivative of the inside, which is dy over dx, okay? Or we could write y prime. Okay, that's usually the notation that's used in implicit differentiation. Okay, we still have equals to 0, we just bring that down, and then it's just a matter of solving for y prime. Okay, when you do that, you just subtract 2x on both sides. Okay, you get 2y prime equals a negative 2x. You can get rid of those 2's, right, and write y prime equals a negative x, and then you just divide by y on both sides. And sorry if I went a little fast there. I'll try to write a little slower so you can catch up if you're falling behind a little bit there. So yeah, you get a y prime equals negative x over y. Okay, that I just tried to draw a rectangle and all of a sudden it turned into a circle. Okay, but yeah, so that's how you do implicit differentiation, right? It literally is just that chain rule kind of idea from before. So let's do one more example. This is the last example of review, and then I promise we'll get into related rates. I just really want you to understand this stuff because it pops up a lot in related rates. Okay, so we want to find y prime if x cubed plus y cubed equals 6xy. Okay, so let's just write our equation out like we did last time, right? That was the same thing. We're following the same process. And we're going to leave room here because the first step after we do that is to take a derivative with respect to x on both sides. Okay? On the left side, we get the first derivative here is going to give us 3x squared. And then remember how we treat y. We take a derivative normally, 3y squared, and then we have to, remember since this is a function of x, we have to multiply by the derivative of that function of x, and we just call that y prime, right? If you really want to get technical about it, right, if this is y as a function of x, we take a derivative, right, that is really just regular dy over dx, right? And you'll see what I mean if I just erase this, right? D over dx of y is the same thing as dy over dx. That's why, if you were confused before when I was writing things like this, that's exactly what I was trying to do. Okay? So hopefully that clears up all the confusion if you're having any. But yeah, so anywho, let's erase this. Let's keep going, because on the right hand side we have to deal with some product rule, okay? And so if we call u 6x and v y, we need to also deal with u prime, which is going to be 6, right? That's just the derivative with respect to x of 6x. And then v prime, which is going to be the derivative of y, which is dy over dx. Okay? Then we just product rule out. We can write as u prime v, 6y, plus v prime u, 6x times dy over dx, or y prime. And then it's just a matter of solving for y prime. And when we do that, right, we just want to get all our y primes to one side first. So we can subtract the 6xy prime on both sides and subtract the 3x squared on both sides. And then we get a 3y squared y prime minus a 6xy prime equals a 6y minus 3x squared. And then we just factor that y prime out because it's in both of these terms here. And you'll see that we get something that we can just end up dividing away. Okay? We divide this on each side. And we can simplify here, right? We have 6's and 3's, so we can write them as 2's and 1's. So we'll do 2y minus x squared over a y squared minus 2x. Okay? So that right there is, a good review of chain rule of implicit differentiation. If you can understand this stuff, right, then if you can understand this stuff, you have all the calculus that you need for related rates. Okay? You'll have all the calculus you need for related rates, and then really all it becomes from there is just following that step-by-step process for related rates, which I will give you in this next problem here. Okay? But make sure, before we move on, make sure all this is sitting well with you. Take a 5-minute break to review if you want, or just take a 5-minute break to stretch, get some water, whatever. Okay? But if you've done that, if you're comfortable, let's move on. Okay, so we have a sphere example here, and this is a perfect opportunity for, this is the same example we had in the red section, but now we're actually going to do it out. This is a great time for me to introduce the step-by-step process for these related rates problems. Okay, it's the step-by-step process that I like to follow. So a spherical water balloon is being filled with water at a rate of 100 centimeters cubed per second. Okay, so we have a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when its current radius is 25 centimeters? And again, maybe it would be better wording. I don't know. You guys let me know. I think it might be better wording if I just write when its radius is 25 centimeters. Okay? But the first step, remember, this whole entire problem is going to be hard if you don't actually know what this looks like, right? And so you want to draw a diagram as the first step. That's what I always do. It's what I recommend you do. Just for a sphere, draw a circle. Okay, this is a spherical water balloon. You know how water balloons expand, right? So this water balloon is going to have some volume. Okay, it's going to be changing, right? And if that volume is changing, then the radius of this water balloon, write it like this, right? That's the radius. That radius is going to be changing. The whole water balloon is going to be expanding outwards. Okay? So there's your diagram. It looks, okay, I'm going to be honest, my diagram looks kind of trash. That R doesn't even look like an R. But hopefully you get the idea. Okay? So the next thing that we really want to do, we want to label everything. Okay? That's step 2. Okay? This was step 1. I will circle it as such. Okay? For step 2, we're trying to label everything here. Let's think about what we were given in the problem. Let's think about, other things that what we want to find, right? And we'll just write that all down. So step 2. We started off, we were given how the volume is changing in time, right? It was the rate at which this balloon is being filled. That is dV/dt. Okay, that's 100 centimeters cubed per second. Okay, we want to find the radius of the balloon, or how fast the radius of the balloon is increasing when the radius is 25 centimeters. So we can write that down too, right? We'll write down that our final rate, or the radius in question, you can write it down as like RF or whatever you want to write down, but that's going to be important to note for later. Okay. Then we also have like, okay, how fast is the radius of the balloon increasing? And that rate would be dr/dt, right? How fast is that radius increasing? And so that's what we don't know. And so there's a good, we've labeled everything now. We're all good. So now we want to find an equation, right? We want to find an equation that will relate volume to the radius, okay? Do we have an equation in mind? Do you have an equation in mind that would actually work for something like that? Well, yeah, the volume of a sphere, right, is right here, third step. I'll write it down here. The volume is going to be 4/3 pi r cubed, right? That is the equation, okay? And now that we have that equation out, right, we have volume and radius related to each other, okay? It doesn't matter that we don't have dV/dt, dr/dt. That comes later, okay? The main goal is, in this problem we have volume and radius. We need to relate them. We did that. So step 4, differentiate your equation. What we want to do now is take a derivative with respect to time, okay? And remember, all of these things are functions of time, right? So that's how this that's why I did that review from before, right? Volume is a function of time. So when you take a derivative with respect to time, you're going to get dV/dt, right? And when you take a derivative of r cubed, right, r is a function of time as well. It changes with time. And so if you take a derivative normally, right, you get 3r squared, but you also have to take a derivative of the inside, right? If r is a function of t, you have to implicitly differentiate, right? You have to get that dr/dt out there, okay? And that is where this should all come together for you, okay? So we differentiate with respect to time on both sides. I'll write it out as such. And then again, it's just going to be dV/dt equals a 4/3 pi times a 3r squared, and then we have to multiply by that dr/dt, right? That's part of taking that derivative of r cubed, right? If we had v squared, right, and we were taking the derivative of that, we would get 2v times dV/dt, right? We have to always have that dV/dt in there, because that's the derivative of the inside. Okay, so we can simplify this a little bit. We get dV/dt is going to give us the 3's cancel, and we get 4 pi r squared dr/dt, right? And well, let's look here. Remember what we're trying to find, right? So the 5th step here is plug in and solve. We can do that pretty easily here. And I'm running out of room, so what I'm going to do is I'm going to move these babies here, pull this up, step 5. Okay, now we wanted to find dr/dt, okay? And we know what dv/dt is, and we know what r is. Well, we know what r is, we know what dv/dt is. So the only unknown in this problem is dr/dt, and that's good because that means we can solve for it. Okay, so we can either substitute in right now, or we can just solve already for dr/dt and then plug in. It really doesn't matter what you do, but I'm just going to start plugging in. So dv/dt we know is 100 centimeters cubed per second. And I'm not sure if your teacher is going to be much of a stickler about units. I don't think mine necessarily was. So yeah, and this dr/dt is supposed to be multiplied there. Okay, when you do it out, right, you divide over that 4 pi and then the 25 centimeters squared. You get dr/dt is going to be 100 centimeters cubed over seconds divided by a 4 pi 25 centimeters squared. And if you just do that math here, you plug that in your calculator, you get that dr over dt is going to give you 0.0127 centimeters per second. Okay, so let's just make sure that we understand what happened with this. Okay, let's just go over our step-by-step one more time, and then hopefully that'll make all the rest of these problems that we're going to go over in this video a lot easier. So the first step, right, we read the problem, okay, we drew a diagram, right? We had to understand what we were looking at, right? Because if we didn't, then all of this other stuff would have became a lot harder. We then proceeded to label everything, right? We figured out, okay, well, we were given dv/dt, we were given r, we want to find dr/dt, and so then, we had a pretty good idea of what we wanted to relate, right? We wanted to relate a change in volume to a change in radius. We needed an equation that was going to allow us to do that, right? And remember, I said don't worry at all about the time derivatives, just worry about what's in here. Right? Worry about relating those two things. How can we relate the volume of a sphere to the radius of a sphere? Okay? That equation, that step 3 thing, right? That what was going to allow us to do that is this volume equation for a sphere. Okay? Then comes in the derivatives. Then we differentiate our equation. We take time derivatives on both sides. Okay? And then once we do that, we end up just implicitly differentiating a little bit. We plug in and solve. That's step 5, right? Step 5 right here. And when we do that, we get dr/dt is 0.0127 centimeters per second. Okay? So that is it for number 1. Now, I do want to note, because I didn't note this earlier, I do have a full Calculus 1 course that by the time you watch this will probably be out. That course is going to have just many more practice problems, and it's going to better able me to help you personally. And so if you want to go check that out, you can check out the links in the description below, and I'll have all that along with my Patreon if you want to go check that out, and I have a bunch of other courses that are coming soon. So anywho, let's move on to problem 2 here. Number 2 is a ladder example. This is very, very, very popular. Okay, so I have the step-by-step process down in here. Hopefully you can still see that. Hopefully the screen doesn't make it too small, but a ladder 10 meters long is leaned up against a wall. The base of the ladder begins to slide away from the wall at a rate of 1 meter per second. How fast is the top of the ladder traveling towards the ground when the base of the ladder is 6 meters from the wall? Okay, so we were given a whole bunch of different things there. Let's try to just read the problem again, understand, right? The ladder's 10 meters long. It's leaned up against a wall. So if you're, the first step, drawing a diagram, right? You think of a wall, the ground, right? And then you have a ladder. Okay, and that ladder is 10 meters long. Cool. That ladder's leaned up against the wall. We have a good picture now. The base of the ladder begins to slide away from the wall at a rate of 1 meter per second. Okay, what does that mean? Well, the base of the ladder, right? This base here is just going to start sliding here at a rate of 1 meter per second. Okay, and we want to see, okay, well, how fast is that top of the ladder going to start traveling downwards, right? That was really the question here, right? Ladder traveling towards the ground. And that's when the base of the ladder is 6 meters from the wall. So there's kind of your little condition there that you have to meet, right? For us in the last problem, that condition was just plugging in the current radius that we were at. So that's what the 6 meters is going to be for us here. Okay, so we actually have a pretty good diagram here, and really, if we want to move on to step 2 and start labeling everything, we can mark up this graph a little bit, this diagram a little bit better. Okay, if we want, we can label this as the x-axis, we can label this as the y-axis, and you can also see that we have a right triangle here, right? And so you might be thinking some Pythagorean theorem stuff that'll come in handy. Okay, but yeah, so that's really what we needed to do to understand this diagram, right? And if we know that we've labeled these y and x, we can start defining what these rates are. Okay, the ladder's 10 meters long. You can just write that as like L equals 10 meters or something. That's a constant. The ladder's not just going to magically change length. If the base is sliding away, right, this is sliding away, that means that the change in x over time is 1 meter per second, right? That's the change in your x direction, and that's what dx dt literally means. It's the velocity, right? And so maybe that's more physicsy, but hopefully that makes sense. How fast is the top of the ladder traveling towards the ground? That is what we're looking for here, and that would be dy over dt, right? How fast is this piece changing? And so that is what we are trying to find here. So now that we have a pretty good idea, let me see if there's anything else we should label here. Yeah, I mean, we could write down like x is going to equal 6 meters here. We're not going to plug that in right away. That's something that we do in step 5 at the very end. Okay. So, and by the way, if you do plug this in right away, it's going to mess up your derivative. So again, wait till step 5 to do that. So now that we have that down, we need to do step 3. We need to find an equation. Okay, what equation is going to relate? Well, what's the two rates we're trying to relate? We're trying to relate a rate of x changing and a relate y changing. Okay, how do we relate x and y? Well, the Pythagorean theorem, right? That's a great way to relate x and y. Okay, the Pythagorean theorem is going to state that x squared plus y squared is going to equal, well, this 10 here, that's a constant, so that's going to equal, you can write that just 100, okay? And again, you could write this as like meters squared, right, because now you've squared this, but you don't, I mean, unless your teacher really cares that much, you don't have to use units, and I'm not going to make you use units for this video because I want this video to be actually enjoyable. So, anyways, we have our equation. Now what we have to do is we have to differentiate, right? That's step 4. We take derivatives with respect to time. Remember, x and y are changing in time, okay? And that's why we are going to need to implicitly differentiate here, because you can think of this as being x of t squared plus y of t squared equals 100, okay? Hopefully I'm not over-explaining things here. I apologize if I am. I'm just really, I want you to understand what's really going on here so these other problems become a lot easier for you. Okay, so take a time derivative on both sides, and then we're just going to start here. So we take a derivative with respect to, we take a derivative of x and y normally, right? So we'll just write 2x and 2y, but remember we need those derivatives of the inside, so we get a dx over dt and we get a dy over dt, right? We're not going to get a dy over dx here because remember, y is not a function of x here. Y is changing in time. Okay, that's what's going on. So there's no dy over dx here. Okay, the derivative with respect to time of a constant is going to give us 0, and so now, yeah, we're set for now. So now we move on to step 5. We plug in. Okay, And you'll notice something here. What were we trying to find in this problem? We wanted to find dy dt. Okay, we know what dx dt was. We know what x is going to be, right? We're trying to find this at x equals 6 meters, but we don't have y. We don't have at whatever this, this state is, right? At this state of this system. We don't know what y is, so we got to find that. Okay, how do we find that? Well, we can use the Pythagorean theorem, right? We know what the hypotenuse is, we know what the x is, so we can just find what the y is. Okay, so let's do that. And then we have no unknowns except for what we're actually trying to find, and that's dy dt. So we'll write down x squared plus y squared equals, well, it's 100, right? That's our equation from before. X here is 6, so that gives us 36. We subtract 36 on both sides. That gives us y squared equals 64, and then hopefully you'd know from there that y equals 8. Okay, so if we have that, we're all set to start plugging in here. Let's do that. When we plug in, we get 2 times 6. dx dt is 1, remember, 1 meter per second. If 2 times a y is 8, dy dt is going to be 0. And then we just start solving here, right? So we can subtract this. That's going to be 12. We subtract that to the other side. That's going to be 16. So we get a 16 dy dt is equal to 12. And actually, it's not going to be 12. It's going to be negative 12. And so we get the dy over dt is going to equal, well, we have a negative 12 over 16. We can divide that by 4 over 4, right? And we get 3/4. And if you want to write that as a decimal, which you can if you're like that, you can. And then make sure you put your units in at the end. And you should know your units would be meters per second, right? Because this is a rate of position changing, right? So it's how position, which is measured in meters, changes in time, which would be per second. Okay. So we can do a quick sanity check there, right? We have a negative sign here, and we know that y is moving downward here, right? Y moving downward is the negative direction, at least what we defined it as. And so, we'll be set there, right? That makes sense. So this answer does make sense, and it is the right answer. I wouldn't just give you guys the wrong answer. All right, so that is it for the second example. We'll move on to our last 4 here, but I do want to note, I don't want you to get burned out in this video. I know I'm talking quite a bit here, so if you want to take a 5-minute break and just come back to the video, that'd be cool. All right, so assuming that you're all set to continue here, let's do a cone example. Okay, basically, we have a water tank in the shape of an inverted circular cone, meaning that's a pretentious way of saying it's upside down. And it's 4 meters tall and has a radius of 2 meters at the base. Okay. If this tank is being filled at a rate of 2 meters cubed per minute, how fast is the water level rising when the water is 3 meters deep? Okay. So there's a lot going on here. We're given a lot more than we usually are, right? And so we just need to start drawing, right? That's the first step. We'll draw a diagram. We'll get this done. So we have a inverted circular cone, upside down circular cone, something like this. Okay. It's got a radius. It's got a height. Okay, we know what those are. We'll plug those in a bit. It's got a volume. Okay, and so yeah, that's really what we're looking at here. That's a good picture. All right, I don't really want to put any numbers up here yet because that's what we can do in step 2, right? We label everything, okay? And basically that means we can start labeling our givens. Okay, so inverted circular cone here, 4 meters tall. That's the first given. 4 meters tall means that h is 4 meters. Okay, that's the total height of the circular cone. We'll see if that comes into play. Maybe it will, maybe it won't. Okay, It has a radius of 2 meters. Good to know. All right. And that's at the base here. So just at the top here, it'll have a radius of 2 meters. Notice that the radius will, it is kind of like increasing as you go up. If this tank is being filled at a rate of, so we have a rate here, that's going to be a derivative. That's changing volume, so will be dV dt. All right, you can get, that's a giveaway because of the meters cubed. So we have a 2 meters cubed per minute. We want to know how fast the water is rising when the water is 3 minutes deep. So that was the last one. Here's this one. We want to know how fast is the water level rising. Okay, so water level, actually, water level rising is dH dt, right? How fast is the water level rising? How fast is H changing? And that's going to be, here's kind of the same condition that we've been given in the last problem. It was that x equals 6 meters at this point. In the problem before that, it was that we had, what was it? When its radius is 25 centimeters. Here, that same exact piece of information is when the water is 3 meters deep. So when H is 3 meters. Okay, so that's going to be important as well. And I know I just have H is 4 meters up here, so we can, if you want to eliminate confusion here, we'll call this H2. Oh, okay. So there's step 2. We're going to find an equation now that's going to relate these things. Okay, so remember here we're trying to relate volume and height. How do we do that? Well, we can use the volume equation, right? Whenever we're using volume, it's probably going to be a volume equation, okay? And that's going to be the volume of a cone. Volume is going to equal 1/3 pi r squared h for a cone, okay? And here's the deal, right? Here's the problem. We can't really, it's going to be hard to take a derivative with respect to time here, right? Not only is the height, right? The height's changing in time, but the radius is kind of also changing depending on where you are on the cone, right? It's also kind of changing in time. And so it would be nice to have just one variable on one side, right? We have the volume on one side and we have the height on the other. And so maybe there's a way that we can get rid of the radius here, and there is. We can do that using similar triangles. Okay, so let me show you what I mean. If we kind of just flatten this cone out, we get a triangle, right? And what you should hopefully realize here, okay, maybe the more intensive way of talking about this is that these things are always going to be proportional, the height and the radius, right? Because they're both decreasing linearly, okay? They're both, it's kind of like y equals some constant times x, so we'll say like 2x, right? This is a line, right? And so y and x are being related here. They're both increasing linearly, I guess. Okay, and so, well, we know that the height of the entire cone is 4 meters. Oh, that's where the height goes. And the radius of the entire cone the radius of the cone at the top is 2 meters. Right? Cool. So we know that ratio between those two has to stay the same. Okay, and so this height right here, h, needs to be similarly, in the same way, proportional to the radius. Okay, and so what we can do here is we can set up a proportion. We know that 2 over 4 needs to equal r over h. It needs to be the same exact idea. And so right now, remember, we want r in terms of h, so we can just plug in h here and just have only h's on this side. Okay, we can do that. So we're solving for r here. We can multiply by h on both sides. Okay, and when we do that, and this is just 1/2, we get that r is going to be h over 2. Oops. Okay, r is h over 2, and we're just going to plug that in now. Okay, volume is 1/3 pi times r is h over 2. We square that, we have h. Okay, and now this is going to be a lot nicer because we only have one variable, right? One variable that's changing with respect to time, not two. We get h squared over 4 here. That gets multiplied by an h. V is 1/3 pi. H cubed over 4, so we can actually write this as 1 over 12, or better yet, pi over 12 times a h cubed. Okay, and now that's step 3, right? We move on to step 4. That's just taking time derivatives, right? We take a time derivative on both sides. Okay, take that time derivative. You should be used to that by now, right? We have dv dt equals a pi over 12. That's just going to stay. And then taking a derivative of h cubed regularly, we would get 3h squared. But remember, h is a function of time, so we also need that dh dt. All right? So we also need that dh dt. Now, it's just going to be a matter of plugging in, right? We know what our dv dt is. We know what that height is that we got to plug in, right? That's 3 meters. Remember, 3 meters. And dv dt is going to be 2 meters cubed per minute. So we have a 2 right here, pi over 12. This is step 5. 3 times h is 3. Square that. dh dt. Just do a little bit of solving here. You get the dh dt is going to equal either 8 over 9 pi meters per minute, or you could also write that as 0.28 meters per minute. Was I writing that before? Yeah, okay, good. Want to make sure I was writing minutes the entire time and not seconds. Okay, so that is your answer for the third problem here, the cone example. Okay, you know, cones can be tricky because you have that similar triangles thing, right? But just remember the reason that why we're doing that, right? We're doing that because we want just one thing, just the height. That changes with respect to time, right? Because r isn't really like a constant, right? It depends on where you are on the cone, right? If you're at the bottom of the cone, the radius is going to be 0, right? Because the tip of the cone, because they're like, that's a point, right? And as you go down to, or I guess up in this case because it's upside down, right? As you go up, that radius is going to increase, okay? But really, it's the same thing here. We just followed that same 5-step process, and that's exactly what we're going to do for the rest of the video. Let's move on to, actually, I think a nicer example. Number 4 is the 2 cars example. Okay, here we have the 2 cars start moving from the same point. Okay, so they originate at the same point. Cool. We can even write that down if you want. Okay, we'll write a dot here. Car A is going to move north at 60 miles per hour. We can draw car A's path. Okay, we can draw this as A. We can label the distance that it has traveled, right? Because that's the rate that we were given. We're probably going to need the distance that it traveled. That's usually how these problems work. And car B is going to move east. Okay, and it gives us a rate for that too. After 2 hours, how fast are these cars moving away from each other, right? What that means is, well, how fast is this hypotenuse changing, right? That's how fast they're moving from each other, because B is moving away in the x direction, right? A is moving away in the y direction, and so if you combine those things, it'd be the rate at which L is changing, right? Because after a while, L will start looking like this. Right, so we want to account for that length change in this line. Okay, so that's step 1, right? I kind of already did it there. We drew a picture, right? We have car A moving this way, car B moving this way. Okay, and now really we're just going to start labeling our givens. Okay, what were we actually given in this problem? And what are we trying to find? Well, hopefully I made it known that dl dt is what we're trying to find here. We're trying to find how the length of that hypotenuse is changing in time. Car A is moving north, right? So that's exactly what dA dt is, right? It's how fast this distance, how fast the car is covering distance, right? So that's 60 miles per hour. And then you have dB dt. That's how fast the car B is moving. Okay? We're also given that these cars are traveling like that for 2 hours. That's going to be important, right? Make sure you write down every single piece of information that you're given in the problem. Okay? Because in this case, right, we don't actually know what A or B are. I don't know if you've noticed that yet, right? But we don't know what those two things are. So the time is going to allow us to find that. Okay? And so we've done step 1 and 2. Let's find an equation, right? And hopefully you can see here an equation that will relate all three of these things, right? That'll relate A and B to L is going to be the Pythagorean theorem here. Okay. So here, yes, we have two things on this side, and actually, if you want me to write this with the L squared on this side, I can do that too. Right? So yeah, we do have two things on this side, whereas last problem, I told you, okay, let's get rid of this r squared, right? Because now we again have two things. But in this case, it's not going to be that bad. These things are being added together. We already have the rates for both of these changing, right? So, I mean, we didn't have dr dt last time, right? So it was kind of annoying. We would have had to do product rule. It would have been gross. There's no sense in going through all that trouble, okay? And so for this problem, it's just going to be some simple derivatives. If you understood the implicit differentiation that we've been doing, this is going to be just the same. Okay, so let's move on to step 4 here. Let's take some derivatives. Okay, if we take a derivative with respect to time of this, we get 2L dL dt. Take a derivative with respect to time on the other side, you just get 2A dA dt plus a 2B dB dt. Okay, so now we should move on to step 5, right? We would be plugging in and solving. But here's the problem. Okay, we're trying to find dL dt. Okay, let's list off the things that we do have. Okay, do we have what L is? No, we don't. We don't have what L is. We do have dA dt, we do have dB dt, but we don't have anything here. We don't have any of those quantities. Right? We don't have L, A, or B. So we need to find those, or else we can't solve for dL dt. Okay? Then you may be wondering, how do we do that? Well, we use the time that we were given. Right? If we say, okay, well, car A was traveling at 60 miles per hour, and it was traveling like that for 2 hours, hours cancel, it traveled 120 miles total. That is going to be A. Do the same thing for B, right? We know that dB dt, right, how fast the car B was traveling was 25 miles an hour. It traveled as well for 2 hours. And so, 50 miles. That's B. Okay? You might be given problems where they have like a staggered start, right? Or, car B starts a half hour later or something like that. Well, the only way that changes everything is you just, you change this, right? Instead of 2 hours, it would have only traveled for 1.5 hours, right? So, there's different variations that they can throw in with a problem like this, but really it ends up being the same idea. So we have A and we have B. Remember, we also needed L. How do we do that? Pythagorean theorem. we can get that L is equal to the square root of a squared plus b squared, right? So the square root of 120 squared plus 50 squared, and that's going to equal 130. I guess I kind of just like lost my notation here, or my units, so whatever. But yeah, so now we get 130 there, and we can solve for L proper, or dLdt right here. So we do 2, I'm just copying from this, right? 2 times L, which is 130, dLdt equals a 2 times A, which is 120, dAdt is going to be, what was it from before? 60 miles an hour, so 60. Okay, we get plus 2 times B is 50, and then 25 is dBdt. Okay, plug in your calculator, do your division, whatever you need to do. dLdt ends up being 65 miles an hour. Okay, so that's that. And by the way, if you were cringing, yeah, you could have canceled out a 2 everywhere. I just didn't because I don't know, I just didn't feel like it today. I guess today was not my day to do that. Okay, so dLdt equals 65 miles an hour. That's that. That is problem 4, right? And again, it's just following that step by step every time. Okay, so we've done another 2 problems. So if you'd like to take a 5-minute break, feel free. You know, I think it'd be a good idea just to reset, and then we'll do our final 2 problems here, and then we'll be done, and hopefully you'll be a lot better with related rates. So now we're going to move on to a triangular prism problem. Okay, for this problem, we have that a water trough is 10 feet long, and it has cross sections that are 3 feet wide at the top and 1 foot tall. Given that the trough is being filled at 12 feet cubed per minute, how fast is the water level changing when the water is 6 inches deep? Okay, so again, that's that same condition that we've been talking about at the end of the problem. That's not going to get factored in right away. It gets factored in step 5. Okay, but we're going to start creating our triangular prism here, right? We know that our did I even say it was a triangular prism in the problem? It's a triangular prism. I probably didn't do a very good job writing this problem, so I apologize for that. Yeah, I never said that. Okay, cool. But it is a triangular prism, so I'll probably end up doing most of the work here for you. For step 1 at least. For the rest of the stuff, we're going to be moving on here. But this is what I meant to say, is that you have this guy here. Oops. What did I do to draw that wrong? Hold up. I gotta be better at drawing for a second here. Let me just draw this one. Oh, I know what I did. No, I don't. I don't know. I don't know why I'm drawing that so horribly. If somebody wants to let me know in the comments, that'd be great. Anywho, so that's a triangular prism, at least it's supposed to be, and it's 10 feet long. Okay, that's how long it is. And so we can label that as like L. If we want to label like this as L. Alright, it's nice to use symbols at first because they'll come in handy later, right? That's 10 feet long, and that's something we'll identify in step 2. Cross sections, right? Which means if we take a slice, right, the slices would be triangles. They're 3 feet wide, so that means it's 3 feet here. Okay, we'll call that 3 feet. I was supposed to say that they're isosceles triangles, so when I said they're that wide, that's what that was supposed to mean. So I apologize, it's kind of a broken problem here. But as long as we get the picture down, you'll be able to solve it just the same. It's also 1 foot high, and so that'll be B, this will be H. Okay, And so we'll, again, identify what all these are in just a second here. Given that the trough is being filled, and so, yeah, we're going to have some volume here too, because that's feet cubed per minute. All right, how fast is the water level changing? So we want to find how fast the water level is changing is dH/dt. Okay, so let's write that all down with 2. We have that our length, how long this trough is, it's 10 feet. We have that the base of the trough, right, the width here is 3 feet. We have that the height is 1 foot. Okay, and we have that our volume is changing. Okay, which, since the volume is changing, that's dV/dt. Gives us the rate for that. That's 12 feet cubed per minute. Okay, and we want to know how fast that water level is changing, and I'll write that as like H2, I guess. And that's 6 inches deep, so that's 0.5 feet. Okay, I apologize if you're like not from the US and you use like meters and stuff. Like I liked using meters a lot more, but like 6 inches is the same thing as half a foot. So yeah. Anywho, so now we got all this stuff. We need to figure out what the heck is going on here, right? What are we have step 2 done, but we need to actually have an equation that relates dV/dt to what we're trying to find in this problem, which is dH/dt, how fast the water level is changing, right? The water level is the height of the water. Okay, so we need to relate volume and height. If we're relating volume, pretty much in any problem, you're going to need to use the volume equation. The volume of a triangular prism, you should be able to figure this one out, right? Volume is like, so like if you think about it, the volume of like a rectangle, or of a rectangular prism, is length times width times height, right? So it's kind of, you can rewrite that as like the area times the height, or the area times the length, or whatever you want to do, right? So what we're going to actually have here, what I'm trying to say is that we're going to have the area of a triangle, right? Those are the cross sections. And then we're just going to extend that. And that's going to be L. So the volume is actually BHL over 2. Okay. Hopefully that makes a little bit of sense. But we're trying to relate V and L here, and we've been able to do that with this volume formula. Okay, but what you'll notice here again, we have the same thing as we did before in the, I believe it was, third problem, right? The cone example, where we have an R squared, we have an H, they both change in time, they're both right next to each other, that'd be really gross. We're not given how R changes in time. Just as in this problem, we're not given how, this base is going to be, kind of like changing as we go up. We got to put that in terms of H, right? We don't have to do the same thing for the length, because the length's constant the entire time, right? No matter where you are in this tank, you can agree that the tank is 10 meters long, right? But you won't be able to agree that the base is 3 feet if you're sitting right here, right? Then you'd say the base is like 1 foot. Okay, so our next goal here is going to be to write B in terms of H. Okay, hopefully you can see that here. Again, we weren't given a rate for B. We're going to use similar triangles here just like we did in the last problem. Okay, so let's just take a little bit of this here. Okay, we're going to take a little bit of this triangle. Okay, actually, this is isosceles, so I'm writing it wrong. Okay, so we know that the base and the height are going to be related here, right? The height The total height of this thing is 1 foot. The base is 3 feet. And so they need to maintain that ratio, right? That's the whole idea with similar triangles. So if you have a triangle down here, right? Another triangle right here. That base needs to have the same ratio to the height. So 1 over 3 needs to equal, right? 1 is the height, 3 is the base. Okay, and so solving for b here, you get that b is equal to just, when you have two fractions equal to each other, you can move things diagonally. And so if we move the b up this way, we move the 3 up this way, we get that b is equal to 3h. Okay. So again, if you don't know that trick, just move the b upwards here, move the 3 upwards here. Okay, b is equal to 3h. That's great. We can plug that in. We get that v is equal to 3h times h L over 2. That's 3h squared L over 2. And if we want to just plug L in now, because it's a constant, L is 10. And so if we plugged in 10, we'd get 30 here, and 30 divided by 2, which is in the denominator, is 15. So we'd get 15 h squared L. No L, because that was the whole point. Okay, so hopefully that makes sense. But now that we have that volume formula, we just have it in terms of h, one variable. It's going to be really nice. Okay, so moving on here to step 4. Step 4 is to differentiate both sides. dv dt, right? That's what we get when we differentiate this. Now we do this with respect to time. Take the derivative as normal, 30h. Then we have to multiply by the derivative of the inside, which is going to be dh dt, right? Because h is a function of time. Okay, just like all that chain rule and implicit differentiation rule, or implicit differentiation stuff that we did as a review in the orange section. Okay, if this is confusing at all to you, definitely go check that section out if you already if you skipped it or anything. Okay, so we have our height, right? That was 0.5 feet. We have our dv dt, that was 12 feet cubed per minute. And now we're just going to be plugging in, finding dh dt. Get 12 equals a 30 times 0.5 dh dt. And if you write what dh dt is, make sure you're using the correct units, right? You can kind of afford to not write any units and be cool if you will know what the units are going to be at the end, right? Here we have a height that is changing in time. Height is measured in meters. Time is measured in this case, minutes. Or sorry, height is measured in feet. Time is measured in minutes in this problem. So we're going to have feet per minute. Okay, and that's your answer. So that, I mean, there's not much to say on this one. It's really, again, just the same kind of deal. The volume is, something you might not have to memorize. Hopefully you can feel that out. Remember, you can just it's the area of the cross sections, right? Just imagine taking a slice down. That's your cross section. Your cross section would be a triangle. Okay, and here I did say it was an isosceles triangle. I don't really think that came much into play in this problem, but nonetheless, you just multiply it by how far you, if you're like into engineering at all, you know what I'm talking about here, how far you've extruded this into the third dimension, how much length you've given it. Okay, so then then you have to do that similar triangles thing, because this is really gross having something like this. If you can get it into all terms of like one variable, that's going to be a lot nicer. Okay, let's move on to our last problem here. Let's get this over with. Okay, we have I can't believe I wrote this much. Okay, so Joe is walking down the street at 4 feet per second. He's minding his business. Well, you can tell I was tired when I wrote this. Okay, Joe's mama is suspicious that Joe is up to no good, and so she has a giant searchlight out in the lawn, 20 feet away from the street. This searchlight turns so that it is always facing Joe. It's that's cool, I guess. I'd love to have a parent like that. If we let theta be the angle between the beam of light and the perpendicular to the path, how fast is the searchlight rotating when Joe is 15 feet away from the point on the street closest to the searchlight? Now, you probably have to read this a couple times for it to actually make sense, because I wrote way too much here. But, in some problems, you're going to get a lot of fluff. I don't even think I mean, this is like all fluff here. I didn't give a single number until, from here to here. So your problems are going to have a lot of fluff. They might not be talking about Joe Mama, but it's still going to be, a lot. There's still going to be fluff that you got to ignore. Okay? So he's walking down the street, and he's walking at 4 feet per second. Okay? So let's just say that this is x, some length x of how far he's walked in some time. Okay? He's got this, this searchlight that's after him. Okay? And this searchlight is 20 feet away from the street. Okay, that's what it says. It's 20 feet away from the street. So we can just, we could have drew that line here, whatever. It doesn't matter, but it's just easiest if we do right here. Okay. The searchlight turns so that it is always facing him. So what's going to happen is this angle theta, right? Let's say that Joe is here, right? This searchlight is going to be turned so he's facing, so it's facing Joe here, right? So first off, you'll notice this is a right triangle. Okay, that's cool. But the angle that this thing sweeps out, right? If it's looking, if you call that 0, right? And this angle to here is called theta. And that's what it says there. It's kind of hard with the terminology, but it says let theta be the angle between the beam of light and the perpendicular to the path. The beam of light is the searchlight, right? So it's going to here. And it's saying and the perpendicular to the path. The perpendicular to the path, right? That's this. So it's the angle in between those two things that I just highlighted. That's theta. Okay. So we want to know how fast the searchlight is rotating. Okay. And note, and one more thing I will say before we hop into step 2. Okay. This is step 1. 20 feet here. Okay. 20 feet is a constant, and that's why I'm not labeling it as like y here or anything, because that's just going to stay the same. Okay, it doesn't change. So step 2, we're going to start labeling, right? We know that at the end of the problem, this is our extra information. Remember, that's what we plug in step 5. We're going to write that at the end, so that's going to be x equals 15 feet. Okay, we know originally that Joe's walking down the street at 4 feet per second. That's dx dt. That's how fast he's changing in the x direction. Okay, that's dx dt. What else do we have? We have that 20 feet. We already wrote that down where it needs to go. And really, we don't have any other information here other than, of course, what we're trying to find here. We want to find, let's see here, how fast the searchlight is rotating, right? And so how fast the searchlight is rotating, how fast something rotates is going to be a change in an angle, right? That's how fast you're doing something like this. That's going to be an angle. Okay, a change in an angle, so that's going to be how theta changes in time. Okay, and that's what we're trying to find here. Okay, so that's cool, right? But now the question is, how do we actually relate x and theta in an equation? Because that's what we're doing, right? We need to find an equation that relates x and theta. Our two rates need to be related. And so we can do that with trig, right? We know what our opposite side is, right? The side that's opposite of the angle. We know our adjacent side. If you think of SOHCAHTOA, right? Tangent gives us opposite and adjacent. And so we can write that the tangent of this angle theta is going to be opposite side, x, over the adjacent side, 20 feet. All right. And so if we want to write this in terms of x right, x equals 20 tangent theta. I'll just drop the units here to make this a little nicer to look at. Okay, so drop it, you get 20 tangent theta. Cool. All right, so now that we've done this, what's next? Well, we can differentiate, right? We have our equation, now we differentiate with respect to time. Okay, we take a time derivative of x, we take a time derivative of 20 tangent theta. Now remember, both of these are changing in time. X is changing in time, theta is changing in time. So they're both functions of time, right? You can write this as x of t to illustrate how x is changing in time. You can write theta of t, so how theta is changing in time, right? And so we need to take our derivatives accordingly. We get that dx dt equals a 20. Derivative of tangent theta is secant squared theta. And then we need to multiply this by a d theta dt. All right, cool. So do we have everything we need to plug in and finally get this problem done? Sadly, no. We have dx dt, we need d theta dt, but we also don't have theta. We have to find what theta is. Okay, and you could do that by, like, you know, again, we have x equals 15 feet, so you could plug in 15 feet here. And if you're allowed to use your calculator for this, you could just take like a inverse tangent on both sides and find what theta is that way. But if you don't have a calculator, which I'm going to assume you don't, because it's always better to assume that you don't have a calculator for a problem, what's actually going to be really cool to do here is, instead of using a tangent, we're going to use a cosine. Here's why. We can rewrite this as dx dt equals 20 times or actually, we could do this. We could do 20 over cosine squared of theta, right? And actually, we can rewrite this as cosine of theta squared, right? That's the same thing. We have a d theta dt here, right? And so here's the deal. Why did I write this like this? Like, why am I doing this? Well, because remember that, like, if you have cosine of the inverse cosine of theta, that's just theta, right? The cosine and the inverse cosine cancel each other out. Well, that's what we can actually get to have happen here. So instead of having an inverse tangent, we can do an inverse cosine. It's going to be a little bit more work, but again, if we don't have a calculator, we're going to have to do it anyway. Okay, so what we're going to do, we know the cosine is adjacent over hypotenuse, so we'll need the hypotenuse here. We'll call that L. Okay, we know that x is 15 feet. So if we write the Pythagorean theorem out, we know that 15 squared plus 20 squared, right, that's the other side, and then the hypotenuse is L squared. So let's see if we can figure out what L is. This would be 225. 20 squared is 400. That would give us L squared. Get 625 is L squared, and hopefully you know that it honestly doesn't matter if you know this or not, but 25 squared is 625. Okay, so L is 25, and that's going to help us find our cosine, right? Cosine of theta is going to be adjacent over hypotenuse, right? The adjacent side, what's next to the angle, is 20 feet. Okay, the hypotenuse is 25 feet, so this is 4 over 5. And that means that, and honestly, like, this is what cosine theta is. It is 4 over 5. So we can actually just plug in 4 over 5 right here already, right? If you want to see that in a different way, you could just solve for theta here. You get that theta is equal to the inverse cosine, right? Just take an inverse cosine on both sides of 4 over 5. And if you just plug in, like I'm about to do here, right, you can plug it in as cosine of the inverse cosine of 4 over 5. And then the whole thing is going to be squared. And then, like, you know, the cosine and the inverse cosine cancel off. And again, you're just left with 4 over 5. So I'll write this a little more cleanly before solving it all at once. And of course, I want to also note that dx dt here is 4 feet per second. So I'll just write that as 4 over 20. we have a 4 over 5 in the denominator. It's going to be a 16 over 25, right? And then we have a d theta dt. Do a little bit of math here, you get what d theta dt actually is. And d theta dt is going to be 0.128 radians per second. Okay, if you have an angle, you're trying to find the change in the angle in time, that's going to be in radians per second. Okay, or radians per whatever time that you have. Okay. Awesome, guys. So that is the related rates video. I hope this helped. I hope I didn't, explain things too much or too little. I really just wanted to give you guys an in-depth understanding of everything that was going on with related rates. Now, if you want, more like this, you want more videos, you want more practice problems, you want to, maybe be able to talk to me one-on-one, just ask me questions, different things like that. I do have my full Calculus 1 course that I definitely recommend you check out in the link in the description. Right now, as I'm recording this video, I'm working on getting that out, but it will be out very, very soon here, and by the time you watch this, it'll probably already be out. So again, you can check that out in the description. Feel free to donate to me on Patreon. That'd be great. Right now, I'm trying to pay for food and rent, so if I can do those two things, I'll be in good shape. But yeah, so I hope this video helped. Subscribe for more, and I'll see you guys next time.